Welcome to Learning to Engineer. What is steady state error and how the different inputs affect the error? We are going to look at this concept in this video. We will also solve some problems to enhance your understanding. If you are already aware of the theory behind that and you just want to glance through some problems, you can make use of the timeline and just jump to the relevant sections. Let's get started. Consider this closed loop system. We have an open loop gain which is g of s and the feedback path transfer function is h of s. Throughout this analysis, we will be considering a unity feedback system. This means that the h of s is 1. For all unity feedback systems, this way of finding steady state error is applicable. For non-unity feedback, what are we going to do? We will explain that in my next video. Okay. So for a unity feedback system, consider that R of s is a unit step input, which means R of t is 1, which is a unit step input, and if you take the Laplace transform, the R of s is 1 by s. So for this input, what will be the output? We will first look at that and find out the error term in it. The transfer function is, this is a negative feedback, so it is g of s divided by 1 plus g of s h of s. This is nothing but g of s divided by 1 plus g of s, since this is a unity feedback system. The error function multiplied by g of s is the output c of s. But what is this error? The error will be the subtraction of the r of s minus c of s into h of s. Let's substitute the value of c of s from this. So what is e of s? This will be the input minus error times the transfer function, the open loop transfer function multiplied by h of s. So now we can separate the terms. We can have the error on the one side and the other term on the other side. So this implies that e of s plus e of s into g of s into h of s equal to r. Okay, so let's take the error term common. E of s into 1 plus g of s into h of s. This is equal to r of s. So what is the error function? R of s divided by 1 plus g of s into h of s. This is the error function. So what are the components that affect this error? The first thing is the input. Next is the product of g and h, which is the system transfer function and the feedback transfer function. Okay. So now we have different inputs. For step input, the magnitude will directly jump to a constant level once the input is switched on. Let us call this as r of t equal to a, and the ramp input is r of t equal to at, and for a parabolic input r of t will be of the format at square. Okay. So we have to find out r of s, which is the Laplace transform. This is a by s, and for ramp input it is a by s square. For parabolic input 2a by s cube. Okay. So this is the value of the input in Laplace domain when we have step, ramp and parabolic inputs. The steady state error will be the error in the output when the system has reached a steady state. When will the system reach steady state? When the time t tends to infinity, the system will reach a steady state, and hence the error term would be e of t at t tends to infinity. So when we talk in terms of Laplacian domain, the steady state error would be the limit s tends to 0, s into e of s. Okay, so this E of S depends upon the system input R of S, which differs for different test signals. First, we will find out that for step input, the ESS for step input would be limit S tends to 0, S into E of S, which is S multiplied by R of S divided by 1 plus G of S H of S. So what is R of S in this case? It is A by S divided by 1 plus G of S into H of S. So the S terms will cancel and the steady state error will be A divided by 1 plus limit S tends to 0 G of S into H of S. So for a ramp input, what is the steady state error? The value of R of S will differ. So we are going to do the same with the R of S, A by S square. So ESS will be limit S tends to 0, S into A by S square divided by 1 plus G of S into H of S. So these two will get cancelled and this what is the steady state error? It is A divided by limit S tends to 0, S into 1 plus G of S H of S. So for ramp input, the steady state error will be A divided by limit S tends to 0, S into 1 plus G of S. For a parabolic input, this would be limit S tends to 0, S into E of S divided by 1 plus G of S into H of S. Okay, what we are doing? We are substituting the different R of S based on the case and finding out the ES as the case is. Okay, so what is the E of S for a parabolic input? It is S into 2A divided by SQ. So these two terms will cancel and the value of ESS will be 2A divided by limit S tends to 0, S square into 1 plus G of S into H of S. So these are the values of steady state error for different kinds of input. Consider a simple pendulum and it's oscillating. Okay, so this system, when it is subjected to a force, the bob moves to the right, then to the left, then to the right, and even after the force is removed, it slowly oscillates and then comes to a rest. It doesn't rest immediately, and of course this is because of acceleration due to gravity, and you would have done this experiment in your school. Correct? So consider this system. The moment you remove the input, you expect a reasonable amount of output, right? And for that output to reach a steady state, it takes some amount of time, and that is called as a transient state. Consider an electrical system. You are charging a capacitor or maybe an inductor. Okay, it takes some amount of time for that to charge and then to discharge. So that little lag you will face when you are getting the final output. The final output means at time t equals to infinity, what is the steady output from the system? And you will have an expected output and the output that is available. The difference between these two is called a steady state error. The output at steady state will be a little different from the set point or the target value of the output that you are expecting. This difference is called as steady state error. We'll put forward the denominator term g of s h of s in a time constant form. We call this form as time constants because it is easier for us to find out the poles and zeros from this format of equations. Okay, about zeros and poles we'll talk about in a separate video. Okay, so what is J? J is called as the type of the system. Okay, so for various system types we will analyze what is going to be the value of this error. First, let us consider a step input. This is not unit step input, this is step input of step size A. Okay, so in that case what's going to be ESS? A divided by 1 plus limit S tends to 0 G of S into H of S. If this is a ramp input, the steady state error is going to be A divided by limit S tends to 0 S into G of S H of S. With parabolic input with size A, the steady state error would be the same term, but it will have a S square in the denominator. S square into G of S into H of S. Okay. Now let's analyze this term. This is called as the positional error constant. This is called as the velocity error constant. This term is called as the acceleration error constant. Why are we defining these terms separately? Because ESS is directly affected by the denominator term, and whatever be the magnitude of the input, it is not the concern. Only the denominator, the error constant Kp, Kv and Ka determines what would be the steady state error, and we are going to study that in detail. Okay, for different cases. Consider this as a type 0 system. Okay, if this is type 0, it is s power 0 over the denominator. Okay, the g of s h of s term will have s power 0 in the denominator, which means it is 1. There is no s term separately. So what will happen when s tends to 0? When s tends to 0, the denominator will be, this term will also be 0 and this term will also be 0. Okay, so what will happen? It is 1 plus 0 into 1 plus 0, which is 1. The denominator will be 1 in this case. And about the numerator, this term will also be 1 plus 0 and this term will also be 1 plus 0. So g of s h of s is simply equal to k, which is the system gain. Thus, for a type 0 system, what will be the steady state error? This will be a constant, okay, which is A divided by 1 plus K, which is a constant. What about a type 1 system? For a type 1 system, this is going to be s power 1, which is s. So, when s tends to 0, this term will become 0. So, g of s h of s is anything divided by 0, which is infinity. Okay. So, for a type 1 system, what will happen? This e of s term will be a divided by 1 plus infinity, which is infinity. So, what will be the error? The error will be 0. Hence, for a type 1 system, if you are supplying a step input, the error will be 0 ideally. But practically, we do have some errors because of some non-linear components, and all these derivations are available, applicable only for linear time invariant system, which is LTI systems. If it is a non-linear component or something else is present inside a system, we cannot account for this because the entire Laplace transform theory is applicable only for a linear system and not for a non-linear system. So, for a type 1 system which is linear, the error will be 0 in case of step input. What about type 2? It's the same, right? If it is a type 2 system, this s will have a power 2 on the denominator, and when s tends to 0, what will happen? This term will go to 0 and hence you will have an infinity term in the denominator again. What happens to e of s? A divided by 1 plus this term. This term tends to infinity in case of type 2 systems. So again this will be a by infinity, which is 0. So for type 0 system alone, you will have a constant error at steady state. For type 1 and type 2 systems, this error will be 0. For a ramp input, let us consider a type 0 system. For a type 0 system, the value of j is 0 and hence s power 0, anything power 0 is 1. So this term will be 1 for a type 0 system. So for a type 0 system, this is going to be, which is 1, and this is also 1, and this is also 1, this is also 1 for a type 0 system. So this is k divided by 1, which is k. G of s, h of s value is k. Okay, so limit s tends to 0, s into k. Okay, so I'll just write the steps for you. This is limit s tends to 0, s into, what is g of s, h of s in this case? K divided by 1. Okay, so when s tends to 0, this is going to be, anything by 0 is infinity, right? So for a type 0 system, the error is infinite. What happens to type 1 system? In a type 1 system, the value of j is 1. So again, this will be s power 1, which is s. Okay, so the value of g of s, h of s is going to be limit s tends to 0, s into g of s, h of s, which is k divided by s. And when s tends to infinity, all these terms will be 1. 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, and all these terms will be 1, and hence g of s, h of s is equal to k by s. So when these two s cancels, we will have a constant error, which is a divided by k, the magnitude of the input divided by the magnitude of the system's gain. Okay, so what about type 2 system? This is going to be a divided by limit s tends to 0, s into k by s square, because you know, understand this, all these terms will be 1 when you put s tends to 0. Okay, so when this is cancelled, what is the denominator term? Infinity. So you will get a by infinity, which is 0. So again, let's do the same for parabolic input. So you need to have this table in mind to find out the error term of different inputs. So you just need to remember this table to solve problems. In short, for a type 0 system and unit step input, you will have a constant error. And for type 1 and type 2 systems, when you are supplying unit step input, you will have 0 error ideally, that is no error at all. So it is better to apply step inputs for type 1 and type 2 systems. When you take a ramp input, you should not apply ramp input to a type 0 system, because the error will be infinite and you don't want that amount of error. For a type 1 system, you have a constant error, and once you know the value of the error, you can adjust the system in such that the error is very minimal. Or for a type 2 system, you can use ramp input, because you are not going to get any errors at all. For a type 2 system, you can apply parabolic input too, but you will have a small amount of error, a by k. If you go for type 1 and type 0 systems, you should not supply ramp input and parabolic input. Okay, so based on this table, you can understand which kind of input to apply for which system. Ideally, you want the error to be 0, right? So when you have a type 1 system, you can supply step input. Even for types 2 systems, you can supply step input, you will get 0 errors. And if it is a type 2 system, you can supply ramp input, because even in ramp input, you won't get errors. When you have a parabolic input supplied to a type 2 system, the error is going to be very small, which is a by k, and you have to provide a correction to minimize that error. But for type 0 and type 1 system, it is safe not to use ramp and parabolic inputs. Okay, so based on this chart, you can understand and apply which kind of inputs should be applied for which kind of systems. We will solve some problems in this concept to understand better. We have a system transfer function that's given to us. We have the open loop and the closed loop transfer function. What is the type of the system and what are all the error constants? The third thing is, what is the error if the input is 4t? This is a ramp input of 4t, and what will be the error of this system when you have this input? We just saw that for a type 1 system, the ramp input will get a constant error a by k. Just by looking at the problem, you should be able to solve this. Okay? This is already in time constant form. So s power j, where j refers to the type of the system, here j equal to 1. So this implies that this is a type 1 system. Okay. So what are all the error constants? First we will find out g of s into h of s. Since it is a unity feedback system, both are same. 40 into s plus 2 divided by s into s plus 1 into s plus 4. Okay, so this is the g of s into h of s. Positional error constant kp is equal to limit s tends to 0 g of s h of s, which is equal to 40 into 2 divided by 0 into 1 into 4. So anything by 0 is infinity. Okay, so what is the value of velocity error constant? This is limit s tends to 0 s into g of s h of s. Correct. So this is going to be s into 40s plus 2 divided by s into s plus 1 into s plus 4. Okay, so these s will be cancelled, and when the limit s tends to 0, this is going to be 40 into 2 divided by 1 into 4. The velocity error constant is, right? What is the acceleration error constant? Just by looking, you should be able to say this is a type 1 system and you multiply that with s square. What will happen? So this is limit s tends to 0, s square into 40 into s plus 2 divided by s into s plus 1 into s plus 4. So this term will cancel and you are going to have a s term in the numerator. When s tends to 0, it is 0 into something. So ultimately Ka is 0. So what is the value of steady state error? In this case, what is the steady state error? Yes, this is going to be a, whatever be the input magnitude, a divided by infinity, 0 error. So in this case, what is ESS? In this case, ESS is a divided by 20, and in this case, it is a by 0 infinity. Okay, so we saw the value of ESS for different kinds of error constants. So they're only asking about the error constants, not about ESS, because for you to know the ESS, you need to know what input is applied, whether it is a step input, unit step, or what. You need to know about the input, only then you can find out the steady state error. They have given that R of t is 4t. This means ramp input is applied and the value of A in this case is 4. Okay, so what is R of S? 4 divided by S square. Right. So this implies that E of S is equal to 4 divided by 20, which is equal to 0.2. Okay. So when you have a ramp input of 4t applied, the steady state error is 0.2. Okay. We'll solve one more problem in the same concept. This is quite a little trickier one, but it's just the same story. Whatever you did in this problem, you're going to do in the second problem also. We'll check that. In this problem, the system transfer function is 10 into s plus 2 divided by s square into s plus 1, and this is a unity feedback system. So h of s is equal to 1. what will be the steady state error when the input applied is this? R of s is equal to 3 by s minus 2 by s square plus 1 by 3s cube. Okay, so this input has a combination of step, ramp and parabolic terms. So you need to find out the error terms separately for the separate inputs. It's just like superposition theorem. Okay, we are considering this to be a sub input 1, this to be a sub input 2 and this to be a sub input 3, and the error because of this is calculated as ESS1, this is ESS2 and this is ESS3. So the ultimate error because of this total input will be the sum of all these errors. Okay, so I recommend you to pause the video at this stage, try it out and find out the steady state error. So clearly, what is the type of the system? This is a type 2 system. So from this, can you tell me, for a type 2 system, which inputs will give you zero error? Step and ramp input, right? So the first two terms of this equation you can right away ignore because the s terms are going to cancel, and so this denominator is going to be infinity and the error is going to be zero, and this happens for the step and ramp input. Only for a parabolic input you will get a constant error which is a by k. Okay, just by looking at this table you should be able to answer this problem. This is a step input. Okay, the step size a is 3 in this case. So what is ESS1? ESS1 is going to be 0, ESS2 is also going to be 0, and the value of ESS3 will be a by k, and what is a in this case? 1 by 3, right? And what is k? This is ka, acceleration error constant. Okay, we will find out this acceleration error constant alone for now. Okay, what is ka? Ka is equal to limit s tends to 0, s square into g of s h of s, which is equal to limit s tends to 0, s square into s plus 1. So these two terms will cancel. So when s tends to 0, this is equal to 10 into 2 divided by 1. So Ka is 20 in this case. What is Ka? Ka is 20. So ESS3 is equal to A divided by Ka, which is equal to 1 by 3 divided by 20. Okay, so this is the value of the steady state error. Okay, so when you are given an input which is a sum of 2 or 3 more terms, you should separate that into step, ramp and parabolic input. How do we do that? 3 by s. When you have a step input, let us say r of t is equal to, let's say 5. What is r of s? 5 by s, right? So with just the denominator term we can find out what kind of input it is and hence find out the steady state error right from the tabular column. Okay, so this is why you need to have the tabular column in mind so that you can solve the problem really quickly. Thanks for watching. Let me know your thoughts in the comment section, and if you have any problem that's difficult for you to solve, you can mail that to learningtoengineer@gmail.com. Thank you.